Welcome to our final video on Year 10 probability. I think it's video 9, it could be video 10, but in this video we're looking at tree diagrams. And because of my love of biology, of course I've popped us a tree in there. And we know that our tree diagrams in maths look like trees, but are showing something very different. So our outcomes for this video. Okay, by the end of the time of watching it and doing a bit of practice, you're going to be able to draw tree diagrams to show the sample space of 2 or more stage experiments. So that means a tree diagram with 2 lots of branches or more. Okay, we're going to understand when it's appropriate to use a tree diagram to display outcomes. You're going to know how to determine the probabilities on tree diagram branches using with or without replacement. So when we're doing that trial, whether we replace our outcome as such, or whether we take it out. And then we're going to be able to find probabilities of an event using a tree diagram. Many of this you may have already done, so some of it will be a bit of revision. So first of all, what is a tree diagram? Well, we've got one here, and I know that you've seen them before because you seemed quite looking forward to having a look at tree diagrams, so that's great. So what have we got here? We're pulling cards from a deck of cards. Now remember, we said we've got 52 cards in our deck. We've got 4 different suits, our diamonds, hearts, spades and clubs, and our diamonds and hearts are our reds, our clubs and our spades are our black cards. And we learned quite a bit in our previous video about our deck of cards. So here we've got our deck of cards. Now our first card we're going to pull, and we're looking at whether it's a diamond or not a diamond. So we've got a 1 in 4 chance of it being diamond because we've got 4 different suits and one of them is a diamonds, which means we've then got 3 out of 4 that's not a diamond. So one important thing to remember with our probability and our tree diagram. All of the branches on one section have to add up to a whole, okay, so the whole set as such. So 1/4 plus 3/4 is a whole, yeah. All right, then over here, these would be 2 branches, so these have to add up to the whole. So what we're looking at is once we've pulled a diamond, we're then replacing it because it's still, we're replacing it, we know that because it's still out the quarter, all right. What's the chance of our second card being a diamond or being not a diamond? So we're pulling one card, then we're pulling a second card. And remembering that all of the probabilities of the tree, the branches, add up to a whole. So I'm not talking all of these, it has to be from their stem, from the one stem as such. Now, when we are finding out the probability of that, so the probability of drawing a diamond then a diamond, we multiply together their 2 probabilities, and what we're doing there is multiplying fractions. So you multiply the denominator by the denominator, that gives us 16, and the numerator by the numerator, 1 by 1 gives us 1. Okay, so a few things we've learned there. I think I'll actually go on to that in a moment. So when do we use tree diagrams? Because they sometimes look a bit complicated, but believe you me, a tree diagram helps us to visualize our more complex probability problems. Okay, so displaying our 2-step experiments. You remember we talked about conditional probability. For example, what is the probability of getting A if B has already occurred? Well, what a mouthful that is, but you can draw that on a tree diagram and it makes a bit more sense. And we can use in our with and without replacement trials. I don't know why I've got capital R on replacement, but when we're saying if we're comparing an experiment with replacement and without replacement, it's actually a really nice visual way to compare that. So tree diagrams are great visuals. They help you to really see your probability problems. So here we've got one for tossing 3 coins. So the chance of a head or a tail with our first coin is there's a 1 in 2 probability, so half probability of getting a head, half of a tail. Then our second coin, the same. Okay, our third coin, the same. Now, if we wanted to know the probability of getting 3 heads in a row, we would multiply the 3 halves together. Okay, if we wanted to know the probability of a head, a tail, then a head, we'd multiply. It's all halves on this because there's a 1 in 2 chance and it's all heads and tails. Okay, so this is just to remind you how we multiply our fractions. So we multiply our denominators by multiply our denominators together. So 2 times 3 gives us our 6, and our numerators together, and that gives us our final fraction. And this is just a visual showing us what we're doing. So we're asking for half multiplied by a third. So what we're actually looking at is half of a third. Okay, and that's our 6. So this is a visual to show you what you're actually doing when you multiply fractions. Okay, so let's think about our 2-step experiment. What is the probability that the first card you select is a diamond and the second one is not a diamond? Okay, so we're looking, first card is a diamond and the second one not a diamond. Okay, so we've got a diamond, not a diamond. So this is going to be our probability. There's a 3 out of 6 chance, 3 out of 16 chance that that we would draw a diamond followed by not a diamond. Okay, let's think about our conditional probability because we've just done that. Looking at that tree diagram, we've just done some conditional probability, but let's talk about it more. So we said if we was looking at the probability of A occurring if B had already occurred, we would look at the total number in the union of the intersect of A and B divided by what's in B. Okay, and then vice versa, if we was looking for the probability of B occurring if A had already occurred. One thing to remember, right, when you're setting this up, what the second value always is your denominator, okay? All right, let's think about that a bit more. So the probability of A occurring if B has already occurred, and this is what that looks like visually. We want to know the probability of A occurring, which is just this section, if B has already occurred. So we're trying to find the probability of their intersect there. Now, here we've been using that as the total, but we can also do it as probability, okay? And basically, that would be then using our fraction, our decimal forms, if we was going to there. All right, this is just the opposite. Ignore the scribbling. I've just not managed to get that gone. Okay, so this is just the opposite, what we spoke about. And here, we're looking at the probability of B occurring if A's already occurred. So there's A all coloured in. And then if B occurred, it would just be the intersect. Okay, so we put A, the total of A is the denominator. And here it is again in this probability form. All right, let's have a look at this. Okay, so we was talking about A and B, yeah, in those examples just there on conditional probability. So here we've got that. We could have A occur, we could have B occur, and then after A could occur or B could occur. Remembering A and B are subsets. They could be anything. They could be flipping a coin and the outcomes of a coin. They could be different cards. They could be numbers on a dice. Okay, they're just different events. These are subsets of our universal set. So let's have a think about this. We've got this tree diagram. The probability of A occurring if B has already occurred. So this is if we're writing it out. B always, that second value is our denominator. All right, so what is the probability of A occurring if B has already occurred? So that's the path we're looking at for that one, because we're asking, what's the probability of this happening after this? Okay, here we've got the opposite. So what's the probability of B occurring if A has already happened? So what am I going to highlight? B occurring, so it's going to be one of these two, because the second thing is the B after A. Hopefully I'm going to highlight those two. Let's have a look. There we go. So it's B occurring after A. Alrighty, so now we've got some fractions involved here. Alrighty, so we want to know the probability. We're going to use this one, B after A, but we're now going to give ourselves some values. Before we do that, what is the intersect? Okay, how can we find our intersect? Well, here it is. Here's our intersect of diamond and diamond. So a quarter times a quarter would be that value. Okay, so a diamond and not a diamond, there's that intersect. Not a diamond and a diamond, and not a diamond and not a diamond. You see how I'm using the complements here? So it's that opposite. Alrighty, so I'm going to look at the probability of not a diamond being pulled after a diamond. So we've got the probability of not a diamond after a diamond. Okay, let's have a look. So the one we are looking for is not a diamond after a diamond here. Okay, that is the one that we are looking for there. That is our intersect. So then we would do 13 divided by 16. Okay, hang on, let's do them. 13 divided by 16 is 0.19. And here, our diamond, well, there's 13 diamond total. Okay, our probability of a diamond is 13 out of 52, yeah? So we would go 13 divided by 52 gives us 0.25. That's how we can work out that probability of a not diamond being pulled after a diamond. Okay, so we had to work out because you can't do a fraction over a fraction. Okay, that's why we work it into its decimal form. All right, let's have a look at an example now. 2 lucky door prizes are randomly awarded to a group of 7 male and 3 female partygoers. Use a tree diagram with branch probabilities to show how selection with replacement can be displayed. So we're doing a tree diagram and we're doing with replacement for that one. Then we're going to do a tree diagram without replacement. Then we're going to find out which has the highest probability. From a male then a female. Okay, one with replacement, one without. We're going to step through each of these step by step. Okay, let's go. So we are looking, that should have come up after, but never mind, my graphics are bad. We're looking at a tree diagram with the branch possibilities to show the selection with replacement. So we've got female, male, first of all. First door prize is either going to go to a female or a male. In total, there are 10 people. So we've got 7 male, 3 female. That makes 10. So there's a 3 out of 10 chance that the door prize would go to a female. There's 7 out of 10 chance it will go to a male first up. All right. Then our second door prize, we're with replacement, so the person's been put back in. There's a 3 out of 10 chance that it would then go to a female, 7 out of 10 chance a male. The same there. Okay. Just look at that, see that that makes sense. Oh dear, what is happening here with what I've now done, I'm glad that finally turned up, I've divided what we had before, oh, terrible. I've divided these fractions to make it into their decimal form. So that's what I've done on this slide. So here they're just in decimal form. Okay, because you saw if you went on to that next step of that conditional probability, it's easier to do it in decimal form. So I have just done that for you. Okay, now we're doing without replacement. Okay, so without replacement. So if, say, a female's drawn, it was still 3 out of 10, but now that person is out of it. Okay, so there's a 2 in 9 chance now of a female being drawn because one of them's gone. There's still 7 males though because the female wasn't drawn, but it's still out of 9 because one person out the whole pot is out. Oh, my graphics aren't working properly. Never mind. Here, all I've done is divided the numerators by the denominators and put it into decimal format for you. And just be aware down here, I've shown the intersections. So the female and the female, the female and the male. Okay, my graphics are better, but I've got a random arrow. Okay, now, which of the situations have the higher probability? Okay, so we've got, this is without replacement, with replacement, because we're remaining on the 10. Now we're looking for male and female. Okay, so we have got that. Now we can take this one step further and work out the conditional probability, but we're actually not going to for this one because we can compare these fractions. Okay, so we're now having a look at the without replacement one. So we're looking, what are we doing? A male and a female. So we had our 7 out of 10, then our 3 out of 9. So we're multiplying them together. That's what we get. And what it's asking us to find out, it's asking us which of these situations have the higher probability. So this one was without replacement, because we've got our 10 and our 9. This was our with replacement because our number of people remains the same. There's a higher probability from the without replacement than there is with replacement. Yeah. Okay, I hope that's shown you some of the ways we can use our tree diagrams. We'll do more practice in class.